I myself was a victim of not paying attention to that. Trying to build an LED driver, very fast LED driver for a.
And you learned it in the hard way.
I learned it the hard way, totally.
Really?
I had the honor of being the last human being on Earth that bought the last units of that LED.
That's a piece for a museum.
Isn't it? Yeah, that's why I'm telling it so proudly. So let's take a seat. We can begin now with the podcast, please.
Thank you, Antonio. Thank you for the coffee. It looks amazing.
My pleasure. My pleasure. So, for a start, let's begin introducing the podcast. Welcome everyone to Coffee and Tech, the podcast powered by coffee and our passion for electronics. And today in this session we have our guest Ignacio de Mendizábal, EMC expert from MITAI. Ignacio, thanks a lot for coming today.
Thank you, Antonio. Thank you for welcoming me here. It's a pleasure.
Our pleasure is too. So today we're going to talk about the PCB design, how the process looks like, and what are the main issues. And I was discussing with a friend a couple of weeks ago that taking into account all the complexities of PCB design, it's almost a miracle. Each PCB that makes it through manufacturing is almost a miracle, right? And I'm very interested in your point of view, because if you think of the ideal flow, right? Mm-hmm. The ideal flow when you are creating a PCB, when you want to develop hardware, you have an idea, you have a set of requirements, right? Functionalities, technical requirements that you need. And that needs to be captured in what, I don't remember who, but someone called it, I really like that name, the napkin sketch.
Yeah.
Right? We used kind of draw some boxes and say, okay, I need these, I need a microcontroller, I need a display, I need power management, right? And then you go create your schematic, you get your BOM, create the layout, route it, send it to manufacturing, and you have your board on your hands, all assembled, all beautiful. But that's ideal, right? That never happens. There are many mistakes that can be done.
That can happen, but the amount of people, the amount of PCBs that actually reach to the market in that situation are just a little,
right?
Little.
I think it has to do also with the complexity. If I am doing some small development board, sure, maybe, right?
Sure, yeah.
And I wanted to hear from you, what issues have you seen in the part of the layout? Since you're an EMC expert, right? What are the main problems that you see when talking about layout and EMC protection? Yeah,
so the main point is that the PCB layout takes a lot of time, so it's one of the critical parts when designing a new PCB. And many people focus just in functionality. But the problem is that it's not enough that the board works, but it also needs to go through a certification before manufacturers can start selling the product to their customers. So that means that people connect one part of the board to another part of the board, and then they just trace some lengths, some tracks from A to B, but they forget that the length of these traces is very important, because traces are not ideal. We would love to have ideal connections, but the problem is that every single connection, they have impedance, finite impedance, and parasitic elements. So these parasitic elements are critical for a good EMC behavior and a good signal integrity. So one of the most underestimated points is the parasitic elements on a PCB, so long traces. So we find that very often.
That's a very good point. I think many engineers, not all of them, a good chunk are very aware of that, but it's hard to conceive somewhat that our traces are actually antennas, right?
Yeah.
Like when you are doing your layout, are connecting, as you said, pin A on IC1 to pin B on IC2. You're not only connecting to send a signal, but you're creating an antenna. To emit and to receive, right?
That's the point. And The thing is, when you say, hey, this trace is very long and you are creating an antenna, many designers say, okay, it's not that long, it's just this. And they don't consider the trace length compared to the wavelength of the signal that they are transmitting. So when they start running numbers, they say, it's not just a little bit longer, it's very much longer than it should be. So they are creating a very, very nice antenna. So the fact is that many PCB designers are very good in unintentional antenna designers.
I'm afraid so. Yeah, I'm afraid so. I attended a talk by Dan Beaker a couple of years ago, expert from NXP, and exactly he was underlining that we have to stop thinking about electrons moving and more about electromagnetic fields, right? How they propagate.
Yeah, that's
through how signals propagate through the board.
Yeah, that's correct. And also that's another problem or another lack of knowledge that we find, that many people learn about electrons moving, but not many people learn about electromagnetic theory, because it's complex, there are many equations involved, so it takes time, and people decide to run away from them. And the reality is that complex PCBs that as we have right now, they work in the middle of the electromagnetic waves and electromagnetic theory. Yeah. So there is no chance. They need to be involved.
There is no other way around it.
No, not at all.
That is very, very interesting. I was discussing a couple of days ago, focused on the previous part, right? The ideation. Because if it were everything ideal, would be wonderful, but when you are in this wonderful flow that I described at the beginning, if you think you go from the idea to a kind of a block diagram or an architecture, that already can incur into different iterations, because the first sketch, the first napkin sketch you might come up with, probably is not. You need to refine it, right? And then you will find out that you need extra functionalities, and then it's super underestimated when you are going from this system architecture to the schematic development, the amount of time that it takes to read all the information.
It's huge.
To figure out, to read all the data sheets, to distinguish, okay, which component do I use, how do I use it, and how do I take into account, for example, EMC considerations, all the layout, which layer stack do I need, and or which passives do I need, right? Which is very, very important. And on top of that, supply chain. Supply chain issues.
That has been very critical in the last years.
Right. It's like I remember reading news about full car manufacturing plants having to stop because they didn't have enough passives. I'm not talking about about passives. So it got pretty dramatic, and that is something that is also greatly overseen in the developing of PCBs. And then in the end, if you think of all the issues when you get all the reading of data sheets that we have somewhat all agreed that it's okay to have a data sheet with 1,000 pages.
Yeah, in a PDF.
On a PDF format, like,
this is what you have to do, and you have to read it, and then design a board first time right.
Exactly, with that, that's why we were saying that it was a miracle. Yeah. It's a miracle to get it through, right? And it's super time consuming. It takes. I was reading more than 50% of the time of the development is invested in things that are respins, having to overcome issues with supply chain, having to overcome issues with wrongly captured schematic, having to overcome issues with emissions, right? And signal integrity problems.
Power integrity,
Exactly, power integrity, right? And in the end, you can try to overcome some with some simulation, but
I mean, that has been a classical solution,
right?
But the problem is that finding the correct, or let's say not correct, but good enough models to simulate everything you need it's very difficult, or I will say impossible. Or if you want to have a perfect simulation model, you are going to spend same or even more time than the development of a real PCB manufacturing and then measuring. So in the end, you need to find always a trade-off, a balance between both situations.
Indeed, and it's a time-consuming solution, right?
Yeah.
It's a very time-consuming solution. I was checking there was a very nice post on LinkedIn. I'm sorry for the engineer who posted it because I forgot the name. But if you find it, follow him, whoever he is.
Maybe
if you find a very nice engineering post on LinkedIn with very good information, follow the person. Share the post, and if that person happens to be me or Ignacio, even better. So reading about issues then on the schematic side, connections that are not properly made, or power connections, for example, right? The power is wrongly connected to the wrong power source. The grounding is so important, and people don't really take it into account.
In EMC is one of the most critical points,
right?
And so in the schematic part, you have this label named ground, and everybody says, okay, it's ground, it's everything connected, and then they go to the PCB and they start to mix grounds or to create 2, 3, 4 ground nets. And because 30 years ago they hear that splitting ground planes was the way to go, and now with high-speed PCBs, it's a very, very bad decision.
Indeed, yeah, because you end up having you end up not defining a proper return path, right, or a proper reference for your signals, and that's super important. Another issue that I found is that sometimes components that have a certain polarity are just placed inverted, the other way around, and then the best thing that can happen is that you won't have EMC problems, that I can tell you, but you're going to burn your PCB. But that's not a solution you might want to apply.
It's not the way we want to follow.
Exactly, and I myself was a victim of not paying attention to that. Trying to build an LED driver, very fast LED driver for a.
And you learned it in the hard way.
I learned it the hard way, totally. Absolutely, I lost a whole month.
Oh, wow.
Yeah, testing LEDs like nothing, and I chose the best LED, and this LED was obsolete. I had the honor of being the last human being on Earth that bought the last units of that LED.
That's a piece for a museum,
isn't it? Yeah, that's why I'm telling it so proudly. But all these type of errors in the end, I was reading good mitigation strategies, right? Like do control version, do proper grounding. That's very important, actually. Give meaningful names.
The problem there is that if you ask 10 people about what is proper grounding, you will get 10 different answers.
Exactly, it's not easy. Give proper names to the nets, right? When you're connecting.
That's critical in the schematic.
That's super important.
Like also that some designers say, okay, this is a very simple schematic, so I don't need to add net names, to add any name, and then they go to the layout and they find that the names are net 1, net 2, net 3, and routing that is horrible.
That's why I find that it's super important, because in the end we have to be aware that a schematic is way more than just capturing the idea. It's a vessel to convey information for whoever comes afterwards, and that comes afterwards can be on the layout side, and for the layout engineer it's going to be much easier, and if there are any EMC issues it's going to be much easier to debug, but also for yourself weeks afterwards, if you have to get back to the schematic and you made yourself the favor, or to all the colleagues, of documenting everything properly.
Yeah, because we as designers or as engineers, that we think that we can do everything.
Exactly, yeah.
We tend to think, this design that I am working on for a month, I am going to remember everything forever. And then you start working in a different project, you come back and you say, what was this PCB for, or what I was trying to do here. So that's why as you say, documenting starts in the schematic. So creating a very neat and clean schematic.
It's super important, and it's time consuming, right? You can ask other colleagues to review it. You have to pay attention to the supply chain info, and that's super. It's a human being in the end.
It's a lot of time.
Yes.
frustration.
Exactly.
in
Can
the
work
end.
as much as effectively as there's a limit to all
Yeah,
that, right?
yeah.
But I wanted to ask you because since, as we said, since in the end, you begin with the schematic, but then you have to put the focus on how everything is routed. And the schematic can be perfectly captured, but then you need to pay a lot of attention on the component placement
Yeah,
and
that's
the
correct.
routing. I want to ask you, what are the main problems that you've seen in PCB development, in layout, in the layout phase, and what would be the mitigation strategies that you
Yeah,
know that
yeah.
would work?
Okay.
What would
Yeah.
you
Yeah, so we
advise?
until now we have seen many different kind of designs. So people coming with power designs, with IoT, many communication systems. So, and even if people come with different backgrounds and different products and different experiences, we are seeing the same type of mistakes. Let's say one time and another time. So the first thing is what I was mentioning before is parasitic elements. So first thing
Yes.
is that every time that you are tracing, that you are routing, that connection has an inductance and has a it's provoking a propagation time. So if you are routing high speed signals, any signal needs some time to go from A to B. So it happens with cars, but it happens with signals. So if you want signals to arrive fast, you need to reduce the distance. So whenever you are planning a PCB, so not even routing, so just planning the placement, take into account the fastest signals. So what are the most critical signals in your design? Like PCI, Ethernet, RAM memories. So these are the most critical ones, and they need to be as close as possible. So that's one of the most common things that we are seeing, like parasitic elements. So it's true that trace length is let's say the most evident to see, because you have a trace and that has this length. And an indirect effect is that people routing or PCBs that have traces very close to the edges. So as we were saying before, that PCB designers are very, very good unintentional antenna designers, because when routing a trace around a PCB edge, all the fields that are generated by this trace, they are going to leave the board. So that means that in the end, if you are measuring radiated emissions, these traces that close to the edge will provoke that you will fail the test. So the best thing is to first to identify critical signals and to connect components very close to each other, and also to avoid always to have traces very close to the edge. So that they go hand by hand. So those are the most critical related to trace length. Also, another thing that we are seeing is that products that go to certification, so that means that they need to go through radiated emissions, conducted emissions, but also immunity test. So that means that the PCBs or systems need to be protected against external interferences. So if you want that your PCB is protected against external interferences, you need to protect them.
Yeah.
So there are many PCBs that lack protections, that they don't have diodes, that they don't have TVS, varistors, or anything to protect the board against power disturbances or signal. So every time that you are designing a new PCB, it's a very good idea to add protections very, very close to the connectors. So then every time that there is an interference coming to the external part that can be provoked by another system, but also by humans because of the carpets.
Sure.
So we are in the same way that we are electrifying people.
Yeah. Here in this office,
Yeah.
if I walk for 5 minutes around, I can charge everyone's phones.
So you are a nice PCB
Yeah,
destroyer.
I am a wonderful PCB destroyer. Yeah,
Perfect. So you need to avoid this by
Exactly.
adding protections to your PCB. And it's very important to add them very close to the connectors. So in this way, related to the first problem, is that the connection from the connector to the protection element should have a very low impedance, very low inductance.
Very important.
So otherwise, the transient is going to go through this parasitic trace, and the induced voltage is going to be higher than it can support. So in the end, the board will be damaged, and that's a sad moment for designers and managers.
That's always a sad. That's a very, very sad moment indeed.
Yeah.
So we've seen essentially to recap a little bit. One very important tip for avoiding crosstalk.
By the way,
right?
the coffee is amazing.
happy that you like it. So we talk kind of how to avoid crosstalk. right? And issues with emitting from the
with-
board out, and
out
also
of the board,
from the board outside towards the board.
That's it. So to add components, to place critical components close to each other, so you avoid signal integrity issues, propagating fields outside the board, and at the same time, every time that you are placing these critical signals, keep some distance between critical signals and not critical signals.
Yep.
So to avoid this, what you were mentioning, that is crosstalk.
Yeah, that's a very good point. Because to get to the origin, the schematic, if in the schematic the engineer hasn't account for this, right? The engineer doesn't have into account EMC issues that could happen in the layout, because in the end, PCB development is a holistic thing. You need to have so many things in mind. And you need to account for this. You need to have this inside your schematic.
And one of the classical problems is that the schematic engineer works in his corner, the layout guy is working in his corner, and then there is an EMC person who needs to who comes later, coming from his dark corner, and then take care of the result. And that, at that point, it's very difficult to take care of EMC.
And in the end, as you said, in the end, so for the schematic engineer, it can be that all connections are ideal. Everything is wonderful, right? And maybe the layout engineer, well, a good seasoned layout engineer will know to place things close to each other. But say, as you said, so the person developing the schematic doesn't take this into account, because everything is ideal. So no diodes to protect, nothing, no ESD protection, right? That would avoid me frying PCB. And then you do the layout, go to manufacturing, and the later you identify the problem, the harder it is to solve, and the more expensive.
It's going to be very expensive.
And God forbid that some problem is discovered when the product is already in the market. And then you need to find alternatives. Take it into account supply chain again, maybe the lead times. And you have to, and this is something that everyone has to take into account, right? Because if you don't capture it from the beginning, the schematic, that error can propagate.
The problem with EMC, and one of the most common problems, is that since it's a set of tests, or it's a process that you do at the end of the manufacturing, or after manufacturing and before start selling, so it's just at the end. Some people start to think about it when they are there. And as you say, it's later you detect it, it's harder it's going to be.
Of course.
And it's going to be expensive and frustrating. And so at this point, it's going to be painful for everybody, for the design engineers, for the EMC people, for managers, and for customers, because if you started already to give some deadlines, and sometimes coming later with 6 months more of lead time, is not a good situation. It's not an easy conversation to have with your customers.
At all. That's a very good point. I was reading on, I think it was lifecycleinsights.com, that more than 50%, 54%, around 50-something% of the PCB projects, they made a survey with, I think, 200 companies, and more than 50% don't meet deadlines, or get overpriced, like they need more money for the same project. So
that's huge for the amount of PCBs and electronic systems that are being sold every day.
It's a lot of money.
Because we ran similar analysis regarding EMC, and we found that more than 70% of PCBs or systems that are being certified that go to the lab for the first time, they fail the test. So that means that they need to go back, redesign, manufacture again, or fix, or do some hot fixes, and then go to the lab again, which is difficult to find a spot. And because they are always full of people, of customers, they are very busy, and of course it's not cheap. So it's a complicated moment.
Absolutely. And what is the point? What is the usability of these techniques for signal integrity? The VS stitching, using tons of VS to connect the grounds. And what will be your take on this VS stitching, VS shielding, and the different ground planes? Ground planes on the outer layers, yes or no?
Wow, that's a tricky question.
That's a big question, eh?
Well, as we were saying before, we will love that connections are ideal, so that when we connect things, okay, I forget because I connected this ground with this ground, and I pour some planes here, and then life is good. But planes, as it happens with traces, they have inductance, they have impedance, they are not ideal. So even if you are connecting two grounds, and in the schematic is the same ground, of course, in reality, if you have a component here in one layer and then the other one here in another one, to go from this point to this point, you have a plane, you have via, so, and they have an inductance and they have some capacitance. So this is going to impact the ground. So the signals ground, the phenomena named ground bouncing, ground bouncing, when you have your reference that should be stable, but then
It jitters.
it moves. So it's not always that the power is moving, for example, or a signal is moving and it has noise. It's because of the reference. So why we use ground stitching is to make this connection as ideal as possible. So the final goal is to always reduce the parasitic inductance. So that should be a post-it, a sticky note that all designers should have on their desk. Reduce the parasitic inductance. And we had vias that are not very separated from each other, so 3-5 millimeters more or less. So to have this inductance to keep this very, very low. So for a regular PCB, distance between vias is not very critical, let's say. So 3-5 rule of thumb, something like this. When you are in the radio frequency, so in designing a real antenna, then you need to take into account the wavelength of your signal, so that the wavelength of the signals that are going out is smaller, or so it's bigger than the distance between vias. So in this way, so you have these vias, and then the signal does not go through the two vias.
Pass through,
And so that's why I like stitching vias, and that's why I like that all my PCBs and PCBs that I see, that they have at least some vias to connect, to keep these ground planes very well connected. And coming back to your question, so if ground planes and the outliers or not, so that's a common question also from PCB designers, because if you take also some application notes, if you take 10, 5 will tell you yes, and 5 other will tell you no. So it's not always an easy question. So the thing is, PCB layout is, PCB stack up is one of the most important points for EMC. And planning a good PCB stack up is critical. It will save you money, time, and routing time, which in the end, I mean, routing a PCB, a complex PCB can take you 1 month or 2 months. So it can be a really, really complex process, really long process. So a good stack up, normally you have internal ground planes. Normally, so for example, if you are using a 4-layer PCB, so that the 2 internal layers are ground planes. So that means that if you are using this kind of a stack up, in the top and the bottom layer, you are going to have signal power. So you will have a lot of traces. So if you pour all the voids with ground planes, you are going to have a lot of islands. So these islands are not going to be very beneficial for you. So I will say that you don't need to pour top bottom if you have very solid ground planes in the internal ones.
Inside the stack up.
Of course, it always depends on the PCB and so on, but I will say that you don't need to do it by default. So always check what kind of stack up are you going with, and but the most important thing is that all your high-speed signals, they have a very, very solid, and when I mean solid is solid, no gaps, no voids, no slots, nothing in the internal layer. So then all the high-speed signals, they have always a reference plane to go over.
Important.
Yeah.
Very, very important. And let's dive a bit deeper into what MITI is doing, because all these are things, are considerations that an engineer needs to have in mind, right, when developing. But it would be great if when I have, say, the first draft of my layout, if I could check for issues, right? Even before reaching the lab.
Yeah.
Right? Because once I've reached the lab, things are written in stone. Things, the PCB is there, right?
Yeah.
I cannot go to the lab with the ODB++, right?
Yeah.
So how does MITI fit in this picture?
Okay. Yeah, very nice question. And I'm happy that you want to check things before manufacturing the PCB, because many people think that it's not possible. So the classical approach is that, as you said, once you manufacture and everything is over, so your PCB is there, you have already paid for it, and you have already built your test setup, and then you go to the lab. And the problem there is that you get feedback only when you go to the lab. And of course, you have a lot of feedback because you have a full EMC test report, and that's amazing. But it's amazing, but very slow, because that means that if there is one test out of 25 or 20 tests, depends on the certification, that fails, that you need to go back and then go back to your office and then design a new PCB and then repeat the cycle. So that means you can have a report saying, hey, there is a capacitor missing here, or it would be nice that this surface is smaller because you are provoking an intended antenna. So in this way, you can work in parallel with other parts of the PCB, and once you have your report, you can correct the power supply part and then upload again the new version. So in this way, we go with you, so that you don't need to wait until the end and wait for the huge feedback before manufacturing.
Oh, that's wonderful. And so, if I'm not wrong, from what I've read, you use AI to evaluate and provide advice, right, on what to change.
Yes.
That's amazing, seeing how AI is changing the way we develop PCBs, because even nowadays, with all the wonderful tools available, they don't veer from they don't go away from this classical strategy, right? And that classical strategy is still time consuming.
Yeah.
Very time consuming. You said that it can take a month, right, or more, with all the back and forth with the lab and respins. And so if I generate my layout and want to check it in beforehand without going through the lab, I give you the files, or the V++ or my board files. And how long would it take from the moment I upload the files until I get the results, the first report?
So since we know the designers, they have very short times, and they need to keep going. So you will have your report in 3 days or less.
That's wonderful. But that's great. Like, if you compare it to 1 month, 3 days is nothing.
That's the thing.
3 days is blinking.
So that's the idea. So that we want to give a small amount of feedback. So that means that we don't need to have a full month to check that. So and in this way, at the end, of course, you will have a lot of feedback about all your process. But the idea is that we don't stop you, so that you can keep your pace.
That is great, because if you think so, I just mentioned how AI is changing the way we develop PCBs, right? We develop hardware. We are at CELUS. We take part, and that's why I was so heavy and I was reading so much on the schematic side. We also use AI to turn, to go from this system architecture, to go from the block diagram to a first prototype, the schematics. You get the schematics and the BOM, all fully connected automatically.
Okay, and really?
Yes, and it's like, essentially, you get to sketch with generic functionalities, and you can add specifications to narrow down, to nail down what you want better. You can select interfaces.
Okay.
I don't know, if you have sensors, you might want to connect them via I2C or SPI or parallel connection, depending on the speed of what you need.
Okay.
And you decide that, and then the system goes and fetches the best solutions, the best applications.
Yeah.
And it gives you the whole EDA project with the schematics, so the whole application, the same way you would see it on a data sheet, when you see the application note, but in EDA format.
Oh, that's amazing.
That's great, and it takes minutes. Say, let's go crazy, 1 hour,
Okay.
instead of weeks or months.
Yeah, because I mean, designers they need to spend a lot of time
Exactly.
reading its data sheet, its connection. Okay, this I square C is compatible with this component, or this SPI. Okay, this bit
Exactly.
is
What's the maximal
compatible.
impedance that I can use for the I
Yeah.
square C?
Or the pull-up
Exactly.
resistors.
The Buddha, which I'm not super proud of admitting, but I will admit before in front of everyone that I have forgotten the pull-up resistors more than once.
Yep,
Um,
I'm guilty.
That's exactly. So essentially, you create, because in the end, when you're putting your blogs and connecting everything, you're creating a search query, right? And you send the search query, and the system, with the help of AI, searches through the library of solutions, which is made of digital data sheets. We have digital twins of all information that is saved, all the information that is encrypted in a data sheet that only a human being can read, write, and go through. You get it, it's digital, and then the AI can go through them, find the best fitting solutions, and provide you in minutes with a schematic and a BOM. And then I could very well imagine, so if I say go a couple of years into the future,
Yeah.
how one engineer could define their system architecture on the CELUS design studio, generate automatically their schematic and the BOM,
Okay.
work
Wow.
on the layout, take the footprints, work on the layout, and then
Yeah.
before testing,
Yeah.
go into Mitai, uploading their files.
Wow, that will make things very fast.
Crazy fast.
Yeah.
Like we're talking maybe in a couple of weeks.
Yeah,
You have shortened to a couple of weeks instead of
yeah.
months.
So you go from a customer specification that sometimes is not, they are not very clean
Yeah,
or
exactly.
clear, and you go from that and you go to a full to a PCB that is fully working and very well prepared for EMC in a few weeks.
That's crazy time saving, and it boosts the capacity in the end of engineering teams, right? Because you don't
Yeah.
need to. You're gonna save the more respins you save, and headaches, the more capacity you.
And iterations with the lab and with the manufacturing house and all these small tasks that designers say, yeah, but it's not going to take me a lot of time. And in the end, you add and you spend 1 month.
It always adds up. Always.
Looking for components or fixing something or measuring just in case.
Yeah.
So all these small things, in the end, makes that your PCB is manufactured like a few months later.
Yeah. So one question, because the Series Design Studio, we're working to output EDA projects compatible with all common
Okay.
EDA tools.
Okay.
Right now, we are able to output files for Eagle and for Altium.
Okay.
Actually,
No,
we're very strong, and also in Altium Designer.
that sounds amazing. Many people are using them.
Exactly, that's good. That's a good start. But my question, what I was wondering is, do you take all formats? Do you have any preference? Do you prefer Java or ODB++, or can any board file be uploaded?
So that's a very good question. And so Gerber is it's very common, and all designers know it because it's the minimum amount of files that they need to send to the fabrication house for manufacturing a PCB. But the problem is that Gerber files are a photography. It's just a picture. And looking back to the history of PCB manufacturing, they are a real picture. So they are good for manufacturing, but they lack the information about nets, and so that means connection between components that are critical for EMC, and also they lack information about components. So we have preference. We are working a lot with ODB++ files, which also
richer.
Yeah, they are richer. They have more data, and they are also being used by manufacturers. So that means that there is a compatibility, and people are somehow familiar with it. So we have this preference. But of course, we are also working with other files like Altium files, Eagle, Allegro boards. So that's not a problem.
You can take
but
everything.
If I have to choose one, I will say that ODB++ is the best. Also because it's a good middle point between sharing
all the information, right?
All the IP information that not everybody is comfortable with, and sharing Gerber files that has no electrical value.
That's a very good point, actually. Now that we came up with the topic of IP came out, we with the design with the CELUS Design Studio, we're going to the launching of the platform is public. So essentially, initially projects are going to be open.
Yep.
In the future, we're planning to have privacy on the projects, which it's very important, right?
So that
you're not gonna develop with an open for everyone.
Okay. So by open, you mean that at the beginning, all the projects created by designers will be publicly available?
Would be publicly available, but we're very aware that's not everyone. Many people won't like that. So you need to have your own repository of projects, right? So that's something that we are shooting at, to have that type of privacy. And at the same time, we are also working on getting SOC Type 1 certification, which is the certification for security with the communications on the cloud. We are hosted on Amazon Web Services, which is 27K certified also. And I wanted to ask you regarding this, how is the IP handled when I upload the files to the platform?
So that's a very good question. And so regarding that point, there is no problem at all, because so there is no need to sign any extra document when you upload files, because in the terms of service that we have in our webpage, there is a non-disclosure agreement, so there is an NDA. So from that side, there is no problem. Everything will be handled securely. So of course the design is on the customer, so there is nothing. Because so they are not designing with us, and also we are using the files to give them assessment. So of course it's not like a present.
Sure, of course.
And regarding security, also we are in the same situation. So we are storing everything in Amazon Web Service here in Germany, which is a strict country regarding security and standards. So regarding that point, there is no problem at all.
That's very important, because in the end, if you are protected with an NDA as a customer, right, and you have the security that you're using Amazon Web Services, I believe here in Germany they have the service in Frankfurt, and the disaster recovery is in Paris, if I'm not wrong.
I don't remember, but I think so.
Don't let me lie to you, nor to the audience.
But they are covered. Yeah.
Exactly. That's very important. And I think with this, I run out of topics. Which is interesting, because this we could be rambling on and on without end. But before our audience falls asleep, I think is a good moment
I think that it's enough for today. We will continue
the podcast
another day.
Thanks a lot, Ignacio, for participating. Thanks a lot. I hope you like the coffee.
Thank you for the coffee. Thank you for inviting me here.
It was
has been a pleasure.
My pleasure also, and well to the audience. Thanks a lot for watching us, and see you in the next session. Bye bye.
Chao.
Bueno, pues no ha quedado tan mal, ¿no?